Today we're going to what we'll call Chapter 6. And here we're going to talk about, and when I say radical functions, I don't mean like they're surfers or something. They're totally radical. What I mean is that they're going to involve like a square root or something. So definition, a radical function can be written in the form y equals a times the nth root of x minus h plus k. So before we go on and like really kind of dive into radical functions, we really need to like familiarize ourselves with this operation, the nth root, and kind of talk about what that means and how to do stuff with it before we can really kind of go any further. So that's going to be like the first quarter or so of this section or this chapter is going to be involved in just kind of getting used to using this operation and kind of how it works. Okay?
Mr. Kulig?
Yes.
Is that a 4?
That's a Y? I don't, H maybe?
Oh, H, okay.
So when we say nth root, we're talking about this symbol here. And this n is called the index. So when n equals 2, and when what we mean by a square root is value b, this implies that b squared is equal to a. So for example, we know the square root of 4 is 2 because 2 squared gives us 4. Is everybody okay with that notion? And again, the square root we should be relatively familiar with. That's an operation we've used a fair bit. I might have come across at some point the cube root. So what the cube root says is that if the cube root of a gives us b, that tells us that b cubed is equal to a. We've seen this just a little bit in this course. So like when we dealt with the difference of two cubes factoring, we observed that 2 to the third is the same thing as 8. That was something that was a piece that often came up when factoring sum or differences of two cubes. So we know that the cube root of 8 must be 2, right? That's a perfect cube that we're familiar with. So that being said, a number like 4 is an example of a perfect square. Would be an example of a perfect cube. So just a little bit of vocab there. So n can say then in general for any integer n greater than 1 that if the nth root of a is equal to b, that implies that b to the n is equal to a, right? Which is just kind of continuing the pattern that we've observed for square roots and cube roots, but kind of extending it for, for n equals 4, 5, 6, 7, 8, etc. Is this okay with you guys? So this, we haven't really done anything. We just kind of set up a little bit of vocab and made sure we clarified exactly kind of what we're meaning in the relationship between like these perfect squares and cubes and these square roots and cube roots, which will become pretty important here in a moment.
What about the end?
So this is just, we're just generalizing what we said for square roots and cube roots.
No, like, oh wait, there we go.
Yep, so we said like for any integer n that's greater than 1, so like 2, 3, 4, 5, 6, 7, that same pattern holds, that if the nth root of a is b, that tells us that b to the n is equal to a. Just like if the square root of 4 was 2, then 2 squared is 4. So just kind of saying, okay, and then that same kind of pattern holds.
Yeah.
That's all. No problem. Okay. So the first quarter of this chapter here is going to be devoted to like simplifying radical expression. 2 areas. So the first area is going to be a radical. The second is going to be multiplying radicals. To basically just do a bunch of examples and kind of talk through kind of how to do this. I'm not going to describe this in general because it's easier to just kind of do it with a bunch of examples, I think. Okay with that plan? Root of 18. So the square root of 18, well, 18 isn't a perfect square, right? I know 18 is between 16, which is 4 squared, and 25, which is 5 squared. And since there's not a whole number between 4 and 5, 18 can't be a perfect square, right? Also, you should just look at that on site and be able to recognize just from what you know about, these relatively small numbers. However, there is a perfect square that's a factor of 18, right? What perfect square is a factor of 18? How about 9, right? I know 18 is the... Everybody's okay there? And now the advantage here is that when I've written these as a product, I can say the square root of 18 is the square root of 9 times the square root of 2. And the square root of 9 is just 3. So the goal here is to basically take something and take out all the perfect squares or the perfect cubes or the perfect that we can. Does that feel okay? Let's do some more examples of doing this, but this is ostensibly what we're going to be working. Does anybody see a perfect square that's a factor of 108? $12 and 9, okay? So 9 is a perfect square. So we can do that. 12 is not a prime number though, right? So it's possible that there's still a perfect square inside of 12 as well. What is it? So 12 we could write as 4 times 3. The other is you can do a prime factorization. 2, right? 108's even, so I know 2 goes in there. 4. What goes into 54? Okay, 9 and 6. Also 2 would have worked, but sure. So 108, is going to be the same thing as So I haven't there yet. Said we can do this. So what times 2 is 4. 3 times 3 is 9. And then I just still have this 3 at the end. That'll come up there sometime when it's ready. Is that okay? And then you can break that up just like times square root 3 gives us 2 times 3 times square root 3 or 6 square root 3. Whenever that wants to show up. There, it finally wanted to show up. Again, either approach is fine. Either approach is fine, no big deal on what you do. Yeah. Okay. Can you repeat what you said? I think between somebody shifted and I missed what you said. So can you just repeat? I didn't catch it all. Okay. Well, if you change your mind, let me know. Or if you're like, nope, I thought I had it, but I don't, like, come back and ask. I'm sorry, I just, something happened and I zoned out for a minute. I got about 2 hours. My daughter was up the entire night, so I'm not functioning at maximum capacity here, so I apologize for missing that. Okay. Do we okay with the square roots here? I mean, it's basically this, right? You just kind of break the thing up into perfect squares, and then you can square root each of those perfect squares separately, and anything that isn't a perfect square just goes back together, right? Let's do one more, and then we'll talk about some cube root examples. Okay? So let's do... Yep. So let's say we have the square root of 1,715. Is that going to show up or not? Can't believe this computer is this terrible. Oh my God. Okay. Do you see perfect squares? So what should we do? Do the prime factorization, right? Yeah. number do we for sure know is going to divide? Sorry guys, I need a minute. What do we know is going to be a divisor of 1715? 5. How do you know that? It ends in a 5 or a 0, right? Yep. So that's 5 and 343. Anybody know what goes into 343? 7 and 49.
Mr. Kulik,
Yes.
this is just another example of prime factorization, right? We didn't miss anything.
I stopped and reloaded everything when I noticed you guys got booted.
Okay.
Yes, sir. 1715 divided by 5. And then 49 is, so I'm just going to call this 49 times 7. So square root 40 times square root 7, or 7. And then square root 5 and square root 7, there's nothing more I can do with those, right? Together as square root 35. Does it feel okay? Let's do cube root 54. Okay, so here, notice that this is now a cube root. Right, we can tell from the index. Notice when there's nothing written in the index, we know it's a perfect square, or it's a square root. The index is 2 if there's nothing written there. So here we're going to be looking for perfect cubes. Do you guys know any perfect cubes? Okay, well then what should we do? Yeah, let's start with the prime factorization then. Yes, sir. 18 times 2 is 36. 16 and 4 is 64. How about just like 2 and 27? Right? Is that okay with everybody? Again, it's even, so I can take a 2 out right away. I usually like to start with the smallies. And then 27, hopefully you recognize that as 9 and 3. And 9 is 3 times 3. So I have 2 times 3 times 3. Everybody agree with that? Now 3 times 3 times 3 is 3 cubed, which is a perfect cube. 3 cubed is 27. So I can say this is 20 times 2, cube root 2.
You'll accept that call.
So that's our final answer there.
I thought you were saying I can either.
Oh, I'm just kind of showing some work. Is that okay with everybody? And you're working something through. What do you got? Okay. Lily?
Okay, so I'm confused between
Okay. Because I know that 27 is 3 cubed. Right? So 27 is a perfect cube, so it's just the cube root is 3. Is that okay?
Yeah.
And I noticed that because I had 3 3s multiplied together, right? So that's 3 cubed. That's a perfect cube. That's what I'm looking for. So the prime factorization should make it easy to find the perfect cubes if you don't know them, because you're just looking for 3 of some number. Or multiple numbers, right? Any packages of 3 that you can find will do. How about the cube root of negative 432? What's different about this problem than any of the previous ones that we've looked at? Landon? It's negative. Now, negative and square roots don't mix, right? That's a problem. We can't take the square root of negative numbers without using imaginary stuff. In this chapter, we're not going to do any imaginaries. Does the same thing true about a cube root, though? Well, let's think about if we can get a negative number if we cube something. So let's just pick negative 1, right? What's negative 1 cubed? Well, that's negative 1 times negative 1 times negative 1, which gives us negative 1. So a negative can still be a perfect cube, right? So can we take the cube roots of negative? Yeah, no problem. So that's going to be kind of, is just to think about it as the negative part and everything else. Cool? Yeah. All right. 432. See any perfect cubes? Okay, let's do a prime factorization and go hunting then. So 2 and 2, 16. Oops. 108 and 2. Okay. How about 4? Why do I want to use 54 there? I already know the answer to that part. So I'm going to save myself some steps and recycle my work from the previous problem. Everybody okay with that? And you'll find that in doing these, you'll often be able to do things like that and kind of shortcut through and steal work from previous problems. And I encourage you to do that. So here what we have, 2 times 2 times 2 times 54, or really 8 times 54. So I
get 3 times 3 cubed 2.
So the cube root of 54 we did in the previous problem.
Yeah.
So I just stole the answer.
Yeah, I know. But then I was so confused on how you got it.
Okay.
Last part, 3 times 3 cubed 2.
Right. So the cube root of 27 is 3. Because 27 is a perfect cube.
Yeah.
Okay. I also want to point out to you guys, just
What's the
FYI,
significance of negative 1?
is 216 is 6 cubed. That's a perfect cube also. So if you'd recognize that. Yep. So would have been a little bit quicker if we noticed that. We didn't. No big deal. I didn't expect you would, as this is the first time you're really having any reason to pay attention to a perfect cube, since it's never been helpful before to you. I don't know why you would notice it.
So if we recognize the 6 cube, what would we do?
Well, at that point, you could just turn this into, cube root, and then you could have cube root 216 and cube root 2, and then this just would have been the 6. So it just, saves you a little bit of factoring or whatever, if you notice that. Again, oftentimes when doing these, there's like kind of lots of little shortcuts depending on how clever you are and what you notice. And But oftentimes you can go and like still get to the right answer if you're doing more than maybe you need to, and you like combine stuff in a funny way and have to uncombine it and rearrange it, and that's not uncommon. Okay. Next up, radicals. And this is really going to be part one. We're going to come back and revisit this a little bit later. Because right now, all we're going to worry about multiplying the same radicals. So like a square root with another square root, a cube root with another cube root. We'll come back later and deal with how we multiply a square root and a cube root or something like that, where they're not the same. But for right now, we're going to ignore that. So let's say we have square root 8 times square root 6. So one way you could approach this would be to start by looking for perfect squares in each radical. So in 8, do you guys see a perfect square? Well, 4 times 2, right?
Yeah.
And 6, do you see a perfect square? Well, it's just 3 times 2. Neither one of those is perfect square, so I'm just going to leave it as the 6. Is that okay with everybody? So I have this, right? The square root of 4 is just 2. Then I can repack the square root 2 and square root 6 together and check again. Is there any perfect squares in square root 12? Well, are either 6 or 2 a perfect square? How about 4 and 3? So that gives me 2 times 3, or 4 root 3. So that's one way we could have approached that problem. Everybody okay on that? Again, nothing really different than the simplifying problems or the reducing problems that we did before, right? You just have more pieces that need reducing, but essentially that's all we're doing. The other way you could have approached this is you could have started by multiplying the 2 together to start with. So 6 times 8 is 48. And then look for perfect squares in here. You might have noticed that 48 is 16 times 3. Oops. Still get you the same spot. Now it appears that this way was faster, right? And when the numbers are relatively small, it probably is. If 6 and 8 were big, like 2 or 3 digit numbers, that may not be terribly effective, because then you have a really nasty prime factorization potentially to get through. So as the numbers get bigger, the first way we've showed you is going to be more effective. If the numbers are small, that second way we did it is probably a little bit more effective. But you can always do it either way. It's a question of how inconvenient you want to make things. But let's do some more, okay? So this is one where I probably wouldn't multiply the 3 together to start with, because you're going to get a pretty big number that it's unlikely you'll be able to pick a perfect square out of. So it doesn't really feel like much of a shortcut to me. Do you guys kind of see that? This is one where I would deal with each one individually, squish them back together, and then see if there's anything else left to deal with. So 27, 9 and 3, good. 12 is 4 and 3. 75 is 25 and 3. Everybody good there? So then I break that all up. So I have 3 root 3, 2 root 3, and 5 root 3. Now, I have 3 square roots here, but I'm only going to stick 2 of them together, because 3 times 3 is 9, and that's another perfect square, but 3 times 3 times 3 is 27. That's not a perfect square. I'd have to just break it back up into 9 and 3 again. So I'm going to just save myself the work and not do that. So I have 3 times 2 times 5, and then I'll have my square root 9 and square root 3. So that gives me 90 root 3. Is that okay? Again, hopefully it doesn't feel too bad. This is all very numeric, so it shouldn't be so abstract as like having to juggle a bunch of variables and stuff around and do a bunch of fancy simplifying yet. Okay, so let's take a look at what we have here. Again, notice these are cube roots, so we're looking for perfect cubes. The smallest perfect cube we know about is 8, and then 27, and then what is 4 is 64, right? Do you guys see any of those? I see an 8 in the 40, right?
Yeah.
So I'm going to go ahead and do that. But the rest of these don't have any perfect cubes in them, right? So I'm going to go ahead and just write them as prime factorizations anyways, because I know I'm going to have to like break them up eventually and kind of recombine them together to make that work. Notice 45 is 9 times 5 and 9 is 3 times 3. That's how I got 3 times 3 times 5 there. I just did that all in my head without drawing the factor tree, because 45 is a times table number. Like, we should hopefully see that pretty easily, right? So I have cube root 8 times cube root 5 times cube root 3, cube root 5, cube root 3, cube root 3, cube root 5. So cube root 8 is a 2. And then cube root 5, and cube root 5. I have 3 5s. That's 5 to the third, right? Which happens to be 125. and then I have 1, 2, 3 cube root 3's. So that's a 3 to the third, which is 27. The cube root of 125 is just 5 because it's 5 to the third. And the cube root of 27 is just 3 because 27 is 3 to the third. So this was just 30. No radicals left. So it turns out that 30 cubed was, if I multiplied those things together, 27,000, which was 40 times 15 times 45. So it turned out maybe multiplying them all together was a good idea. I don't know if you would have recognized 27,000 as a perfect cube. 27 times 1,000 would have been realistic, right? 27 is 3 to the third. 1,000 is 10 to the third. Maybe you notice that, maybe you don't. But it wasn't too bad to do it just the way we did it, right? By just turning everything into a prime factorization, recollecting things. How do you guys feel about this idea? Feels okay?
Yeah.
We're going to stop here. I don't want to do too much here on the first day. This skill, if we don't have good mastery of it, makes everything else kind of